Welcome guys in this new lecture of learning quantum computing using Python series. In previous lecture we learned what is quantum computing, what is Qubit 0, what is the fundamental library of Qiskit, how to install Qiskit, how to install its dependencies, how to install classical emulator so that we can run quantum codes on our local machine, assuming it to be a quantum computer. In today's lecture, we are going to start with our first logic gate of quantum computing, that is called Pauli's gate. So it is nothing but NOT gate in quantum computers. It flips 0 to 1 and 1 to 0. I have written a simple code here to display image in Google Colab. So we have three types of Pauli gate. Pauli X Gate, which is nothing but NOT gate of classical computing. Then we have Pauli Y Gate. It introduces phase change. There is no such analogy in classical computing. Then we have Pauli Z Gate. It introduces change in the phase. So these are the three types of Pauli gate. These form the fundamental gates of quantum computing here. And this is the circuit diagram of Pauli X Gate, that is quantum NOT gate here. So we have Q, which is quantum bit, we have C, which is classical bit. Quantum bit is applied to this X gate. It will change it to 1 or it will change it to 0. Then we have a measurement gate to measure the quantum state, because we cannot measure qubit when it is in random state or uncertain state. This down arrow shows that the result will be stored in 0th index position of classical bit, and then this classical bit is of 1 bit here. So this is the basic interpretation of this circuit diagram. In today's lecture we'll learn about creating qubit 1, that is Pauli X Gate. The libraries will be same that we used for creating qubit 0. We'll be needing that simulator, we'll be needing this quantum circuit, this transpile to translate and compile our code. And basically the entire code is same that we used to create qubit 0. We need qubit quantum circuit 1, 1, which means first is 1 bit quantum qubit and second one is the 1 bit classical bit. Then we need to store the result at 0th position, and then we need to draw this circuit. We need the basic simulator, we need the transpile to translate and compile our code, and then we are going to run that circuit. So this is the exact code of creation of qubit 0. Now let's create qubit 1. For that we'll be needing our Pauli's X Gate. So let me just write the comment here, apply Pauli's X Gate, which is nothing but NOT gate. And again remember why we are needing this, because in quantum computing by default the bit or qubit is 0. So we need to explicitly convert this to 1, which is done by applying a NOT gate. It is just similar to applying logic NOT gate in classical computing. So when we write qc.x bracket 0, it means that we want to explicitly convert 0 to 1 using Pauli's X Gate. So let me write here, by default qubit is 0 in quantum computing. Okay, so this line has to be introduced in the previous code, and now you can see here this X has been introduced in the circuit, and you can see the output also 1. Earlier it was 0, now it is 1. So we have successfully applied NOT gate here. In coming lecture we will be seeing about Pauli's Y gate and Pauli's Z gate also. For the time being we learn what is Pauli's X gate, and that's it for this lecture. Thank you.